In this video, we will talk about the equilibrium constant and how we can use it along with what we call an ice table to determine the amount of any reagents left after an equilibrium has been established. As a reminder, in our equilibrium calculations, we now assume that we do not have a quantitative reaction, that a reaction does not proceed 100%. Now, when there's no limiting reagents, we actually need to do a little bit more complex math to determine the stoichiometry. Luckily, we can use what we call an ice table to help us do the math. The ice in ice table stands for initial, I, change, C, and equilibrium, E. Here is an example of an ice table. On the left-hand side, the left column, we have the initial concentration, the change, and the equilibrium. On the top row, we have the different species present. We have the hydrogen as a reactant, along with iodine, and hydrogen iodine. I recommend that you also write in the coefficient on the top row of the ice table to remind yourself of the balance equation. We can then start filling in our ice table by reading the question. It says, consider reaction equation for the formation of hydrogen, iodine at 448 degrees C. Assume the reaction is begun with 1 mole per liter concentration of both H2 and I2. Right there, we can figure out that the initial concentration of H2 is 1, and the initial concentration of iodine is 1 as well. It did not tell us anything about hydrogen iodine, so that we know our concentration is 0 initially. Let's continue reading the question. Construct an ice table, determine equilibrium concentrated reagent. The equilibrium concentration of I2 is 0.22 millimoles per liter. So then we can fill in this cell right here, the equilibrium concentration of I2 to be 0.22 millimoles per liter. We've now set up our ice table, and we can use this for our problem solving, which we'll do on the next slide. Here in the top part, we have our table that we did on the previous slide. I will let you read all the information here on your own if you pause the video, but I will continue filling in the rest of the ice table based on stoichiometry. Now, we are told that the equilibrium concentration of iodine is 0.22. However, initially you had a 1 millimole per liter concentration. In order for the concentration to go from 1 to 0.22, it must have lost 0.78 millimoles per liter. Notice I put in a negative sign to denote it has been lost. We can now use stoichiometry to fill in other values in the same column. If we lost 0.78 millimoles per liter of iodine, then we also would have lost 0.78 millimoles per liter of hydrogen, because the coefficient, the balance coefficient, is 1 to 1. So we can write here negative 0.78. So if we started initially with 1 millimole of hydrogen and we lost 0.78, then at the end of the day, at the equilibrium value, we have 0.22 millimoles per liter. Now let's look at the hydrogen iodine. Now remember, in the balance equation, the coefficient for hydrogen iodine is 2. So I encourage you to write the coefficient on the top row of our ice table just to remind you of that. Now, if we had lost 0.78 millimole per liter of iodine, then we would have gained twice the amount, because the coefficient here is 2. So therefore, we should put in a value of 1.6 millimoles per liter, and we're going to gain it, so it's a positive value. Initially, we had no hydrogen iodine, but now we gain 1.6 millimoles per liter. So the equilibrium concentration of hydrogen iodine would be 1.6 millimoles per liter. And here at the bottom of our slide, we have our fully completed ice table, and the values they have match what we just determined on the top of this slide. Besides creating an ice table, another essential skill is determining the equilibrium constant for any reaction. The equilibrium constant is abbreviated as Kc. For any balanced reaction, the equilibrium law constant is products divided by reactants. However, you'll notice that there are coefficients here that we put in as an exponential value in our equilibrium expression. So therefore, it is essential that you start off with a balanced equation and not to forget to raise the concentration of all the chemical species by the coefficient of that species in the balanced chemical equation. This equilibrium constant is going to be the same over a range of different concentrations. However, this constant will only be the same at any one given temperature. It is important to realize that all of the concentrations can be measured in moles per liter or millimoles per liter, and that at different temperatures, the value of the equilibrium constant will change. Let's look at an example in determining the equilibrium law expression. We're asked to find the equilibrium law expression for the reaction of nitrogen monoxide with oxygen gas produces nitrogen dioxide. Here is our balance equation. 2NO plus O2 yields 2NO2. Remember, in an equilibrium expression is always going to be the product over the reactants. So in our equilibrium expression, it is going to be the concentration. Remember, concentration is denoted in square brackets. Concentration of NO2 squared because the coefficient of NO2 is 2, all divided by the concentration of NO, again squared because the coefficient is 2, times the concentration of oxygen gas. In Chemistry 30, we will need to put in units for all the concentrations. However, the equilibrium expression, it can be written without any units. And lastly, if you were to write the reverse reaction, the equilibrium expression would merely be inverted. So for the reaction of 2NO2 yielding 2NO plus O2, the equilibrium expression would be the concentration of NO squared times the concentration of O2, all divided by the concentration of NO2 squared. We now have an example of where we use the inverse of the equilibrium constant to determine the equilibrium constant of the reverse reaction. Here we are told that the K value for the formation of HI from hydrogen and iodine is 40. What is the K for the decomposition reaction of the same reaction? So it is merely the inverse of 1 over 40, which is 0.025. Notice that in a forward reaction, for the formation reaction, the K is relatively large, at 40. That means that the products are favored, so that you will get a lot of HI. And then in the reverse reaction, the equilibrium constant is very small, 0.025. That means that the forward reaction, as written, is not favored, and that the reactants will be the predominant species when the system reaches an equilibrium. It is important to note that in our equilibrium expression, we only include species whose concentration can change. So for things like solids or precipitates, or pure liquid such as water, we do not include those species in our equilibrium expression. As an example, we are asked to find the equilibrium law expression for the decomposition of solid ammonium chloride to gaseous ammonia and gaseous hydrogen chloride. In our equation, we have solid ammonium chloride breaking down into gaseous ammonia and gaseous HCl. Because ammonium chloride is a solid, we will not include it in our equilibrium expression. So our equilibrium expression is just the concentration of ammonia gas multiplied by the concentration of hydrogen chloride gas divided by 1. And again, in this case, the 1 is our invisible 1, so this is our final equilibrium expression. As a reminder, all of these concentration values in our equilibrium expressions can be measured in moles per liter or millimoles per liter. However, in our value for Kc, it can be unitless. We do not have to write any units for the Kc because it's often very complex, and while we're learning equilibrium expressions, it is best to ignore the units in the equilibrium constant. Another point of interest for equilibrium expressions is that we do not include any spectator ions. We just include the net ionic equation, because any spectator ions will be both present in the numerator and the denominator, and they will cancel out. Therefore, it is better, more simple, to not write them in the first place. In this example, we're asked to determine the equilibrium expression for the reaction of zinc in copper chloride solution. Our net ionic equation is zinc ion plus copper ions yielding copper solid and zinc ion. Notice that chloride is not included in this net ionic equation. Therefore, in our equilibrium expression, it is just zinc ions divided by chloride ions. We do not include the solids because their concentration do not change, and we do not include chloride. So our equilibrium expression for this example is quite simple. It is just zinc ion divided by the concentration of copper ion. Now let's put our ice table knowledge as well as our equilibrium expression knowledge together in one last example. Chlorine and carbon monoxide gases are mixed in a 1 liter container and the following equilibrium is established. First of all, notice that we're told we have a 1 liter container. It is important to note the size of the container because all of our calculations are based on concentration and not strict mole to mole ratio. Therefore, you have to enter values of concentration into your ice table. Here we're told initially you have 1.5 moles of chlorine along with 2.55 moles of carbon monoxide. We're not told how much CoCl2 we have, so we can assume a value of 0 initially. And then at equilibrium, we have 0.8 moles of CoCl2. And we're asked to find the ice table and then to calculate the Kc of the reaction. On the next slide, we will create the ice table. So let's now look at our ice table. We're told we have 1.5 moles of chlorine. So we can enter that value into our ice table under the initial concentration, right? Remember, it's per 1 liter of chlorine gas. And we're also told we have 2.55 moles of carbon monoxide. So our concentration is 2.55 moles per liter. We're not told of any CoCl2, so we can assume a value of 0 initially. And lastly, at equilibrium, we're told we have 0.80 moles of CoCl2. So we can enter our concentration of CoCl2 as 0.8 moles per liter. And now we have to find all of the other values. It is easiest to find the missing values if there are two knowns. And here we can see we have two knowns. Initially, we had 0 amount of CoCl2. But in the end, we have 0.8. Therefore, it stands to reason we must have gained 0.80 moles of CoCl2 during the change. And if we gained 0.08 moles of CoCl2, then we must have lost 0.80 moles per liter of Cl2 and 0.80 moles per liter of CO. Remember, I encourage you to write even the invisible 1 coefficient in the top row of your ice table to remind yourself of the stoichiometric ratio. Now lastly, we just have to add the change amount into the initial amount. So then when we add 2.55 with negative 0.8, we know our equilibrium concentration of CO will be 1.75. Similarly, when we add 1.50 with negative 0.80, our equilibrium concentration of Cl2 is 0.7. And we were told that the equilibrium concentration of CoCl2 is 0.80. Therefore, we now know the equilibrium concentration of all three chemical species. Now we can enter our equilibrium values, or equilibrium concentrations, into our equilibrium expression. Remember, for this equation, the equilibrium expression is going to be the concentration of CoCl2 divided by the concentration of carbon monoxide multiplied by the concentration of Cl2. And now we substitute all those values that we determined in our ice table into our equilibrium expression and do our math. We find that the equilibrium constant will be 0.65. It is a relatively small number, therefore we know that the reactants are actually favored in this reaction. Lastly, just a few summary points about the equilibrium expression. The constant only gives you a measure of the position at the equilibrium. It does not tell you how fast the reaction occurs. The equilibrium constant is true over significant ranges of concentration. The only thing that changes it is the temperature of the reaction. Pure substances such as solids or pure liquids are not included in our equilibrium expression. Gases and dissolved substances can change their concentration, so we always include them in our equilibrium expression. And lastly, the larger the K, the equilibrium constant, it means that the products will be favored.